As you can see, we have a tire set up on a turntable with a bolt and wing nut to keep the tire stable throughout the process. We use our fluorescent light from the ink analysis portion of the project to light up the tire. We make sure to take the video from a 90-degree angle, and we turn the video into one long image to better analyze the tire's markings and unique characteristics. This is the image of how we artificially aged the ink samples. We printed out a 4x4 grid of black, red, blue, and yellow ink, and we had them under a UVA reptile heating lamp for 0, 12, 36, and 48-hour increments using a sheet of aluminum foil to isolate which samples were receiving light at that time.
This is our setup for the ink analysis with the spectrometer. We have a box that is painted black on the inside with a trash bag over it to prevent all outside light from getting in. This is the reading that we're getting on our spectrometer using the Theramino software. I'm going to select the average button so that it averages out the wavelengths that we're getting to get a average wavelength and magnitude at that wavelength as shown there when I select the wavelength there, the dominant wavelength. And on the inside of the box, we have our sample being measured, and we also have a fluorescent light bulb to provide a good source of light for our reading while also blocking out all outside light.
This is a picture of the X-Rite spectrophotometer we used. This records the LAB values, L being lightness, 0 being black, white is 100, A stands for red-green value, and B stands for the blue-yellow value. We took special interest in the lightness value, as you'll see later, where we initially hypothesized that the lightness value would increase over time with more and more UVA exposure. This is the data we recorded for the ink analysis using a spectrophotometer and the spectrometer. We used different time increments of 0, 12, 36, and 48 hours on different ink samples, all printer ink, black, blue, red, and yellow. As you can see, we measured the wavelength and amplitude, both in nanometers using the spectrometer, and then we remeasured the LAB values using the spectrophotometer. After we recorded our data, we decided to graph to see if we could notice any correlation. We graphed the UVA exposure and the lightness value for the spectrophotometer, and the UVA exposure and the amplitude for the spectrometer. As you can see for the graph on the left, the lightness value from 0 to 100, 0 being the darkest, 100 being the lightest, we saw no noticeable change. And then on the right, the only value we did see change was the blue ink. The amplitude decreased over time. Other than that, we didn't notice any correlation. We conclude that this could be due to the spectrometers not being sensitive enough, and we don't think that the light exposure was insignificant due to the 48 hours of straight UVA light and the excess amount of energy that it was exposed to. This is the energy exposure for the ink sample calculation. We used a 100 watt UVA light bulb with 0, 12, 36, and 48-hour time intervals at a 6-inch distance. We first calculated the intensity by dividing the power by the area casted by the light bulb. We then used that value to calculate the energy exposure for each time interval, and we found that the energy exposure should be dramatic enough to cause a difference in the either LAB values, amplitude, wavelength, or all three. In the future, we hope to graph this difference and be able to predict artificial ink aging to be used in forensic applications. Until then, we think that the root issue is the spectrometers or the spectrophotometers, because we believe that the ink samples have received enough energy exposure to make a difference. Thank you.